Drop testing of the C-69, the Constellation, to determine the structural strength of this large aircraft was performed in the Static Test Laboratory at Wright Field. The airplane, weighing 75,000 pounds, was hoisted and dropped several times from varying distances above the floor. The traveling crane, with a span of 170 feet, is one of the largest of its type in the world, with a lifting capacity of 150 tons. All interior fittings on the aircraft were removed to facilitate later inspections of the fuselage structure. Heavy shot bags battened to the floor represent the weight of those fittings, plus the weight of fuel and payload or passengers. At engine stations along the wings, the 4 Wright R-3350 engines have also been replaced by equal weights of steel plates and I-beams, bolted to the engine supports. Instruments sensitive to all acceleration and landing gear loads are placed at scores of test stations throughout the aircraft and connected by cables to the main test instrument panels, where the impact loads are registered and recorded photographically during each test drop. Motion picture cameras operating at both normal and high speed also record the action of the airplane and gear during each drop. When the fuselage is hoisted 46 inches, the landing gear extends the wheels to 27 inches above the floor, and 75,000 pounds of airplane takes an impact load of 250,000 pounds. This impact equals a drop landing in flight of 12 feet per second. The movement of all shock struts is checked. The nose gear took a 52,000 pound bump, while each of the main landing gears withstood 100,000 pounds impact. Slow motion cameras record the impact on the main gear. Slow motion pictures focused on the nose gear analyze the shock movement and recoil. The final drop was made from a height 3 inches above the required 27 inches. The wing, tail, and fuselage structures show no failures. These tests prove the C-69 was able to withstand more than the required test impact. This low-level night pilotage trainer was developed as a result of the great losses to our invasion forces in Sicily and in Normandy. Well before VJ Day, it was readied for Operation Coronet, the intended invasion of Japan's home islands. With this improved means of terrain identification training, low-level flight is simulated by a moving terrain, with all contours, elevations, and details complete for identification. The full-scale mock-up of a troop carrier's cockpit is moved laterally to the movement of the terrain. This simulates off-course conditions and enables the pilot to correct his flight path for a perfect drop over any predetermined drop zone. Coordinating with this simulated flight, a matching aerial map of the terrain is wound on spools in a small viewer, which is held in the co-pilot's lap. This map, traveling over a fluorescent screen in the same direction as the moving terrain, can be wound through by hand or by a small electric motor with variable speeds to synchronize with the passing terrain. In this course of terrain identification, the pilot and co-pilot are checked out as a team. Since such training is chiefly for night missions, when moonlight affords limited visibility, the room lights are turned out, leaving only the illumination from one small lamp to simulate the proper quality and amount of moonlit visibility. In a matter of 5 or 6 minutes, the eyes of the pilots become accustomed to this semi-darkness. Then, with map movement coordinated with ground speed, it is not difficult to identify any points on the terrain, with such points selected as outstanding on the map. Having identified several checkpoints, airspeed can be reduced before sighting the drop zone. In this instance, the final checkpoint is located at a sharp bend in a river, just to the right of a small town, which could represent the DZ for paratroop landings or cargo drops. For peacetime use, this device offers day or night identification training for flights over new routes not yet improved with beacon and radio installations. The XB-42 is a new departure in design. Although only one-third the size of our biggest bombers and needing a crew of only 3 men, it is capable of long-range performance comparable to our present-day 4-engined aircraft. Built to fly an 8,000-pound bomb load, the range of the XB-42 is indicated by its ability to carry a 2,000-pound bomb 4,500 miles. The long-range capabilities of this airplane have been achieved by its design rather than by an increase in horsepower. The plane is powered by 2 standard Allison V1710 engines. The engines are housed inside the fuselage instead of on the wings, thus eliminating the air resistance of nacelles. The greater aerodynamic efficiency obtained by elimination of nacelle drag and the laminar flow design of both the wings and fuselage are the keys to the achievements of the XB-42. The propellers are counter-rotating and operate separately, each propeller run by an engine. The 2 engines, located directly behind the cockpit, are connected to the propellers by long coaxial shafts. In the event of engine failure, the plane is easily capable of maintaining flight with only 1 propeller. The lower fin of the tail section, besides its role as a control surface, also serves to protect the propellers in case of a bad landing. Placement of the propellers in the rear of the plane has several advantages. It eliminates air disturbances of the conventional front or wing propeller, diminishes the noise heard in the cockpit, and increases the stability of flight by helping to prevent pitch and yaw of the plane. If an emergency forces the crew to bail out, the propellers can be jettisoned immediately. The bomb bay doors operate hydraulically and provide enough clearance for the passage of an 8,000-pound blockbuster. 2 wing turrets are the principal armament of the XB-42. The wing fairing opens to allow freedom of operation. These turrets are remotely controlled by the relief pilot and fire only to the rear. The landing gear pivots backward and inward to become completely housed inside the fuselage. Hydraulically operated, this new technique of retraction eliminates the conventional wheel well in the wing and thereby both strengthens the wing and allows a laminar flow. This method of retraction is also used on the XB-43. This is the XB-43, a jet-propelled version of the XB-42. Except for a few minor changes necessitated by the switch to jet engines, the design is the same as that of 42. It is powered by 2 TG-180 turbine engines, located in the same places as the engines of 42. The hinged sections of the fuselage make the engines readily available for maintenance work. Rammed air for the turbine engines is provided by 2 air ducts, 1 on each side, installed flush with the skin of the fuselage. Retaining all the load-carrying abilities of the XB-42, it is expected that this jet version will increase the speed of this type design aircraft to 506 miles an hour at sea level. With the advent of the XB-42 and 43, combining as they do a reduction in flying personnel, a more economical use of fuel, faster production possibilities, a challenge is presented to our present thinking on large aircraft. This plane may lead the way to a new era in design.